Okay, so I suppose I'll get started. I welcome you to this problem solving and live interaction session for the subject engineering mechanics offered by Professor K. Ramesh in the Swayam portal. So today we will be discussing the contents of week 10, which has to do with rotating frames of reference. Okay, so let us take a look at the first question. So the question says, an object moving, let me say it up front, I'm feeling a little under the weather, I'm not feeling 100%. So if there is any deficiency in the delivery, so I request you to please bear with it. Anyway, yeah, welcome. So we'll get started. So if you look at the first question, it says an object moving with 1.2 meters moving with 1.2 meters along the slot traces a spiral curve when the slotted disk rotates with an angular velocity of 3 radians per second as shown. So we have been given that this is the omega, and inside this slot this object is having a constant velocity relative to this slot as 1.2 meters per second. So the question asks, the Coriolis acceleration vector is a constant vector for the given case since since its magnitude is 7.2 meters per second squared. So if we see A Coriolis, we know it is 2 omega cross VREL. So here if we see the Coriolis vector will be always invariably perpendicular to the relative velocity. So if we see when the relative velocity is this way, omega will be this way. At the next instant, when the relative velocity will be pointing like that, Coriolis component will be pointing like that. Either that or that depending on the angular velocity. So only its magnitude is constant, its velocity is not constant. Only its magnitude is constant, its direction is not constant. Excuse me. So this will come to 2 into 3, 3k cap, since it is clockwise, anti-clockwise. And then we have VREL as 1.2. If I take this to be I, let us say I take this to be I and that to be J. Okay, so this is I cap. So this gives me 6 into 1.2, which is 7.2. 7.2 J cap is my Coriolis acceleration vector. However, it is not a constant vector since this axis itself is changing with the rotation of the disk. So this is not correct. So I hope that that is clear. Are you able to hear me all right, Mr. Stephen? Could you just confirm that? Yeah, okay, thank you. Okay, so let us take a look at this question. Two observers, A and B, throw objects pointing towards C. So we have C here, and then these two observers, they just throw some object pointing towards C while rotating with this disk. Consider the object, so this disk is rotating. Consider the objects to have no acceleration in the horizontal plane once released. If both the observers notice the path of the objects as that they respectively threw, as shown. So what this says is this person B threw an object like this, and then the path the person observed was like that. Similarly, the uh, the object that person A threw, it was pointing towards that, but the path observed by that person was like this. So if this is the case, the disk must have been rotating in which direction is the question. So if we have two choices, so let us go with one choice initially. So let us assume that omega of the disk is like that. Let us say it is like that. Okay. So in such a case, given that there is no acceleration, so the actual acceleration of the ball is 0 of the object. I'm calling it a ball. You can call it the object or whatever it is. Actual acceleration is 0. And if you solve for this, what it will give you is the other components aside, because if you take this to be, there will be a centripetal acceleration acting like that, which will get cancelled with the remaining portion. So what this will come to is, now we know that omega of the object is omega cross r plus alpha cross r with the datum. This will be with respect to one datum. Let us say I fix my datum at O cross r plus 2 omega cross vrel plus arel. So now this is moving with a, since no information has been given, we take it this does not exist. In such a case, no matter where we fix our frame from, this component will always be pointing towards or away from that line. That is, if we mark our datum here, so this will always be pointing like that, either this way or that way, and it will cancel out. In such a case, the only acceleration that can be perceived by the observer, it has to be perpendicular to that path. Only then it will lead to a velocity change which is actually observed by that observer in this direction. So in this direction, it would have to have some acceleration component like that. So that is only brought about by these two components. And we have been given that the actual acceleration of the object is 0. So what does this imply? So this implies 2 omega cross vrel plus a relative is actually summing up to 0. What does ARL mean? ARL is the acceleration perceived by the observer rotating. That is, whatever acceleration is being perceived by A and B, that is ARL. Whereas, due to the virtue of the motion, actually there is a Coriolis component acting. So, if we solve for this, what does this come out to be? So, ARL will actually be the negative of the Coriolis component. That is what they will observe. So in such a case, let us say that I take my omega to be this way, and let us start with person A. Now person A's VREL is like this, and omega is like that. So if this is VREL and this is omega, so omega cross VREL, we can see that it will be pointing towards that. Actual Coriolis component of that object will be pointing towards that. Whereas whatever the person will perceive, we have seen that it will be the negative of that Coriolis component. Coriolis component. In such a case, it will appear this way. So that is what is causing VREL to appear to change in this path. Whereas in actual space, it will be traveling in this path without any acceleration. Now we have checked this for A. Now we know that this disk is rigid. So it cannot contradict. That is, if both these paths are not consistent with our direction, that means the observation made by at least one of them is not correct. Now let us see if this is the VREL that is observed by VREL that was given to the object by B, and omega is this way. Can we see that omega cross VREL will be this way? In such a case, what will the person observe? It will be, the person will be perceiving negative of this, which means that is also making sense. So these two directions are consistent with this omega. Hence, omega is rotating in this direction. So that we can conclude from this, given these paths are reported correctly. In such a case, yeah, Yeah. Huh. No, no. What I said is, yeah, see, Coriolis component we know is this. We know this is the Coriolis component. So the actually, I think what question you had asked was whether there was a arrangement like this where there was a point which was attached to this point, this link. So he had asked, what if I rotate with this? Will there be any Coriolis component? What I had mentioned was, unless when you are rotating with that object, unless you actually perceive a non-zero VREL, there is no requirement for a Coriolis correction. Whereas in case of a slotted disk, if you a slotted member, if you see, actually VREL will exist along the slot. In such a case, because of non-zero VREL, if you are rotating with it, you need to adjust for that Coriolis component. I'm not sure. Yeah. Okay. Yeah. 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 Sorry. This is addition. This is not. I'm sorry about that. Actually, the relative velocity, how we have developed. First, you attach a point, its acceleration, and then from there you perceive thereon. So first we attach a point. From there, other things will appear to rotate. Will have a centripetal acceleration. Then there will be one tangential acceleration. These three will be only there for a non-rotating translating axis. When rotation comes in, there are two more terms coming into the acceleration. So like that, it is developed. So this was a plus, not a cross product. Yeah. Yes. Yes. All these are linear accelerations only. Yeah. Yeah. Okay. Yeah. Yeah. Okay. Very well. So let us look at this problem. This is similar to what we discussed just now. Just that this member in our previous session was like that, and it was pinned here. Something like that was the arrangement. So when this pin and this slider is connected to member CD, where CD is behaving like the crank, in such a case, VC is always known. The absolute velocity of C, the absolute acceleration of C is always known. It is only what we observe from this rotating frame is what will give the kinematical quantities for this member. That is the idea behind this. And why we use this invariably is because there are some quantities which we will know only relatively. So only relative quantities we will know. In such a case, if we have to apply our kinetic equations, then it has to be from an absolute reference. In such a case, from relative velocity to absolute velocity, we go by employing the rotating frame of reference. Anyway, so link CD is having angular motion as shown. So this is having angular motion as shown. Okay. And since omega is not given, we take it that it is 0. I'm sorry, not omega, alpha. Okay, so omega of CD is given to be 2 radians per second. So let us see about how to assign the directions in a moment. Answer the following questions with respect to the xy coordinate axes whose positive directions are as shown. So it is given that this is positive x and this is positive y. In such a case, can we see that x cross y goes into the plane of the paper? In such a case, k positive k cap is into the screen, not coming out of the screen. What does that mean? That means whichever rotation, for example, this rotation, if you see it from the right hand, this thing, it will have an axis which is going into the plane of the paper. So this will be considered as positive here. I hope that is clear. So if this is x, this is y, then all rotations like this will be deemed as positive because its axis according to the right hand rule is uh, coincident with the positive z axis. Whereas in this case, x cross y is going into the plane, so this is the positive direction. In such a case, we can see that omega is actually minus. Omega CD, if we see, it is rotating in the counterclockwise direction, which for this question is negative. Very well. Whether this information will be used, we will see. Yeah, this is this is clockwise, this is anti-clockwise, right? I'm talking about this, how to label this velocity with respect to this axis. Yeah, yes, exactly. But whether this system fits like this, is it like this? It's not like this, right? Because we can see this is y, whereas this is x. So there is a, it is flipped. That is why it is pointing into the plane of the paper. So I should actually qualify that also. You are right. So why don't I do that instead? If this is x, this is y, let us say. Here this is positive. Here this is negative. I hope that is clear now. And this is the case. This is the current case in our problem. Yeah. Yes. So actually how we see the coordinate system is x cross y is z. We will cyclically take it. So x cross y has to be along, will give positive z. So here if we see x cross y will actually give a z that is pointing into the plane of the paper. Hence, if you see this direction, its axis is coming out of the plane. That is why this is negative for this specific coordinate system. Yeah, problem has this axis. Okay, and then when I upload this, I will clarify this a little more and maybe upload so that anyway, yeah. So let us see what have we been asked. If Vc is the absolute velocity of pin C, so this is the pin C. If Vc is the absolute velocity, then the x component of Vc, y component of Vc is asked. So now we have to note what x and y components are. So this is the x component actually. This is the positive x direction. This is the positive y direction. So if we see, if this is rotating like this, I need not go by vector analysis to find out that actual velocity of C will be like that. Because this is r, so omega cross r will be like that. So this is the absolute velocity of C. However, we have not been asked the magnitude, we have been asked the component form. So first let us come up with the magnitude. What is the magnitude? Vc magnitude is nothing but 2 into 0.75. So this will give us 1.5 meters per second, which is pointing in this direction. Now it is just a matter of resolving it into x and y. So we know what is x, what is y. So can we see from the figure that it will have a component like that along x, along negative x, and a component like that along positive y. So what will this be? If this is 60 degrees, if this is 60, then this angle also has to be 60, in which case this has to be 30 degrees. So this is 30 degree. So the x component, if we see, it is nothing but Vc cos 30, and this is minus I cap. Why? Because this is pointing in this direction, whereas positive x is pointing like that. So this is this component. And what will the opposite component be? We can write it easily. This will be Vc sin 30 j cap, and this will be positive because it is like that, and our positive axis is also like that. So in that case, we can write this. So it is minus 1.5 into cos 30. So this is x component is minus, what is that? 1.5 cos 30, which is equal to minus 1.3 meters per second. And y component is 1.5 sin 30, which is equal to 0.75 meters per second. So therefore, VC vector from our coordinate system, which is rotating with that link AB, will be minus 1.3 I plus 0.75 j cap. So this is our velocity of C, absolute velocity of C. Now it might beg a question why we are doing this circus. It is straightforward that we can see where absolute velocity of VC is already known. Now why at all are we doing this? It is to actually find out the angular kinematical quantities for this member AB by attaching a relative rotating frame of reference to that. So similarly, the magnitude of angular velocity of link AB is asked. Okay, now this is link AB. This is our link AB. And we have seen we have attached a rotating frame of reference XY to that. X is like that, Y is like that. Now, when this rotates like this, can we gauge that this will actually have a rotation like that? Since VC is moving like that, naturally this point has to move here at this instant, in which case the link is having omega like this. If we are not able to gauge it from the question, we always have the convenience of considering it to be in the positive direction. If our answer finally comes out to be negative, our assumed direction is needs to be reversed. So that is a given. But to do it that way will be a little dry. It is also helpful if we can actually visualize how things move. So if this is moving like that, it has a component like that, which means that omega AB will be of that nature. And can we see that nature implies that it is along the positive k cap. Since this is clockwise, and for this system, anti-clockwise is negative, clockwise is positive. So omega AB, so let me add a page here. So we will have omega AB is actually omega AB k cap, where omega AB, its magnitude is still unknown. That is what we are trying to find out. Okay, so now how to go about this? Now we know absolute velocity of C. If we were to observe C from our rotating frame of reference at A, let us say, in such a case, from the rotating frame of reference attached to AB, so velocity of C is velocity of A plus omega AB cross RC with respect to A plus VREL. This VREL is coming because we are dealing with rotating frames of reference. Otherwise, only for non-rotating translating axis, we will be having only this much. Okay. Now we know from the question that VA is hinged. So time and again, I will write these quantities, but it is not necessary that they will exist. They may well be zero, but for the sake of completeness, I'm writing it. So this is actually zero in the problem. This quantity is zero. Okay, so what is VC? VC, we know it is minus 1.3 I plus 0.75 J cap. Can we substitute omega AB K cap cross? Now, what is RC with respect to A? Let us see. First, let us find out these two quantities. First, let us find things about these two quantities and then we'll go for the analysis. So RC with respect to A, now that we have fixed it to this frame itself, what is RC with respect to A? It will have only one component along Y, along J. which is 1.2 j cap. So RC with respect to A is actually just 1.2 j. And another thing from our coincident point analysis, we know that the actual curve of C will be like that. The actual movement of C will be along like that. Whereas what we perceive from the RFR is the fictitious point. In such a case, we will see a relative velocity like that. Relative velocity will be along the along the slot. This is actually similar to a slot. We are having a collar that is running over a member. Instead, if we have a slot in the member and a pin runs into that slot, it is one and the same. So AB is actually behaving like a slotted member, in which case our velocity, relative velocity will be always along that slot, given that it is straight. So in such a case, about VREL, we know that VREL vector actually will be VREL, the magnitude J cap. Let me take that to be positive for now, although I know it will be along, I don't know whether it will be positive or negative. That will depend on the problem. So let me take it like this. So this much I know. Now what are the unknowns? See, with this equation, we can solve at best two unknowns. Why? Because we can group I terms together, we can group J terms together. So with that gives us two equations. So we can only solve for two unknowns. What are the unknowns here? This is not an unknown because this is 0. This is completely known from our first part. Do we know RC with respect to A completely? Yes, we do. Do we know VREL completely? We only know the direction, we don't know its magnitude. Similarly, omega AB, we have assumed one direction, we don't know the magnitude. If by solving omega AB's value comes out to be negative, it implies it was along minus k cap, that is all. So we have two equations and two unknowns, so we can comfortably solve for this. So let us go about doing that. So VC is 0 plus omega AB k cap cross R is 1.2 j plus VREL j cap. So from here, what does this give us? Plus 0.75 j gives us k cross j is minus I, omega AB I. So I, j, k cross j is minus I. All, when we go this way, it will all be positive, it will all be negative. Okay. So this is minus I plus VREL j. So grouping I and j terms, we can see minus 1.3 is equal to minus 1.2 omega AB. This is one equation, and 0.75 is equal to VREL. Now we saw that this we could easily do from our actual coincident point analysis. We were quickly able to see that this is the component that is actually VREL, because this is parallel and its value is omega VC sin 30 is actually 0.75. That is what we have got from vector analysis also. So then it begs the question, why are we doing this at all? Why can't we do with coincident points alone? Because when we go for accelerations, it will become more involved. To be sure, we can do it with vector algebra, and we should have different methods at our disposal to apply as and when we need, as and at our discretion. So that is why we are learning this method. Anyway, so VREL we have got, this is 0.75. From here, omega AB come out to be minus 1.3 by minus 1.2, which is 1.083 k cap. So it is positive. That does not imply that it is clockwise or anti-clockwise. It is positive only implies that whatever direction we assume to start with is correct. And since we assumed the direction to be this, which for this system, for this coordinate system is positive, it makes sense. Actually, does it make sense physically? If this rotates like this, naturally this will, at the next instant, it will be something like that. So it makes sense that it will rotate like this, and VREL will be along that. So these two are fine. All right. So we have got the magnitude as 1.083 meters per, sorry, radians per second. And VREL has not been asked. Anyway, we have calculated it very well. So if AC is the absolute acceleration of point C in meters per second, then X component and Y component. Whatever we did for velocity, now we are doing it for acceleration. So let me erase this for the time being. Okay. Now we know that since nothing is mentioned in the question, we take it that this is constant. Omega is constant. In such a case, will C be having any tangential acceleration? There is no alpha, in which case alpha cross r is 0. However, since this is a rigid object and this is rotating like this, it will have a centripetal acceleration pointing like that, whose magnitude will be omega square r. So its magnitude will be omega square r. So this is the actual case. Let me take its copy actually and put it here. So I have acceleration of C. This is the acceleration of C, actual acceleration of C vector, which is omega CD squared r. C with respect to D. What does this come out to be? 2 square into 0.75. So 4 into 3 by 4. So this will be 3. Okay, 2 squared into, so this is 3 meters per second squared. But we have been asked this in the component form and component form of x and y. So let us resolve this. So we know, let me take this color. There will be one component like that, and then there will be another component like that. So this component, this is along positive x, and this is, what is this angle? If we know this is 60, then this is 30, in which case this comes out to be 3, or rather AC sine 30, and this will come out to be AC cos 30. So therefore, acceleration of C, the actual vector, is AC sine 30. So 3 by 2, 1.5 I plus 3 into cos 30. So this will be 2.59 J. So we have got the absolute acceleration of C. Similar to velocity, where we were able to calculate the angular velocity of link AB based on the information of absolute velocity of C. Similarly, we will calculate angular acceleration of AB with respect to this. Anyway, so we have got this. So this is 1.5 I plus 2.59 J. So where is that? Yeah. So this is 1.5 I and this is 2.59 J. Okay. The magnitude of angular acceleration of the link AB is asked. Okay. So how can we go about doing that? Let us see. Now we know from RFR analysis again. Rotating frame of reference to AB. If we perceive C, then acceleration of C is actually acceleration of A plus omega AB cross R C with respect to A plus alpha AB R C with respect to A. But since this is rotating and VREL is non-zero, we have to account for AB cross VREL plus AREL. Will AREL exist? We don't know. It could. What will the direction of AREL be? Since VREL is like this, AREL would have to be along the slot only. If this was a curved member, then AREL can have two components, whereas here its relative acceleration can only be in that direction. If we rotate with this, we will see the velocity only along y. So AREL also has to be only along y. At best, it can change only its magnitude. So from here, we know this is 0. Since this is a hinge, fixed hinge. It's a hinge. Yeah, let me not say fixed hinge because it will create confusion. Anyway. So from here, we know AREL is nothing but AREL J cap. We don't know the magnitude, but we know it is along J. VREL, we know it is 0.75 J. Omega AB, we just found out omega AB was, what was that? 1.083 K. What other things remain? Acceleration of C, we have found that out completely here. There's only one quantity that remains, which is what is asked, angular acceleration of AB. So let us take angular acceleration of AB. Let angular acceleration of AB be alpha AB K cap, where this is the magnitude. So we will assume this also to be along positive K. So let us go about substituting. Substituting, we get this quantity. So I'll remove this. So this is equal to, we have this omega cross omega cross R. What is R? RC with respect to A, we've already found it is, what was that? Where is it? Here. 1.2 J plus alpha AB K cross 1.2 J plus 2 omega cross VREL plus AREL. So now it is just a matter of two unknowns, two equations, two unknowns. Are there two unknowns? There's only one unknown. No, there are two unknowns, sorry. Alpha and AREL. So two equations, two unknowns. So it is just a matter of solving this. So let me simplify this a little bit. So this will be 1.5i plus 2.59 j is, what will this be? It will be 1.083 into 1.2. So minus 1.4074 j. A cross j is minus 1.2 alpha ABI. Because j is, again this will be I. 2 into 1.083 into 0.75. So this will be minus 1.6245i plus ARL J. So if I group again the I terms and J terms, what does this come out to be? Minus 1.2 alpha AB minus 1.6245. This is I plus ARL minus 1.4074 J. So can I calculate AB from the here? 1.5 is, so alpha AB comes out to be 1.5 is minus 1.x. 60 k cap, and the other one is 2.59 is coming out to be 4. So I encourage you to check this once because I'm also solving it live. So there could be some calculation here and there. So please check it. Anyway, when I'll be posting this, I'll ensure that the answers are correct. But since I'm solving it live, there is always a possibility of some numbers mix up here. But the actual purpose of this session is to show how to solve rather than focusing on the numbers. So I hope that is the takeaway for you. Anyway, now we have solved this. So this comes to 4. 4 is what we are getting. I'll check this. You can also check this at your convenience. So one more additional, sorry, this is 2.6 we are getting. This is not 4 is ARL. This is 2.6 magnitude we have been asked. So I take it that this is okay. Then what is it that we have seen from this question? So we have seen that when there are two components connected like this, like a crank and this arrangement. So when there is a point on the crank whose velocity and absolute acceleration is always known. Now it is our task to find out what are the kinematical quantities for the slotted arm, slotted member. In such a case, we will once the absolute velocity and accelerations are known, we will connect and attach a rotating frame of reference to this member and observe the same. In the process of solving, by grouping I and j terms, we can actually find out the kinematical quantities for that very length. So that is the entire purpose of this analysis. So I take it that this is clear. Yeah. So let us look at this question now. So a circular slotted disc. So we have a disc which has a slot which is that curve is circle is what it is saying. So a circular slotted disc rotates with an angular velocity and angular acceleration as shown. So we can see both are along positive k. So actually for the disc, omega of the disc is how much it is 0.4 k cap, and alpha for the disc is 0.1. This is also k, positive k. So these two quantities are given. All right. At the instant depicted, it is known that a ping pong ball P is moving at a constant speed of 1.2 meters parallel to y-axis. So how have we connected the axis? So this is our x, this is our y. It follows that x cross y is z and positive direction is shown correctly. And this velocity at this instant, it is parallel to y. Okay. So if this is parallel to y, what we are saying is this is 90 and this is our position vector. Okay, parallel to y measured relative to the disk. See, this ping pong ball is moving with a constant speed of 1.5 parallel like this with a speed of 1.2, and this is with relative to the disk. So only relatively we know. What the absolute velocity we don't know. Uh, Measured relative to the disk along the circular slot centered at O. So the center of this circular slot is also the disk center, which need not always be the case. So for example, in the previous week, we saw there was a disk like this. Its ICR was here, whereas its center was here, whereas the center of this velocity, if you see, it is somewhere else. So the center for this circular arc is the same as the center of the disk. So this is what is given in the question. From the question, we also know R of P with respect to O. What is this? This is a vector like that, which is nothing but 0.45 I. This much I know because this is along I cap. So, all right. So this is something I know. Now, what have we been asked to calculate here? Been asked to calculate the magnitude of the absolute velocity of P, the magnitude of the Coriolis acceleration of P, the magnitude of absolute acceleration of P. Okay. So now from our RFR analysis, attaching the RFR to the disk, we can see velocity of T. Absolute velocity of P is absolute velocity of O plus omega disk cross R P with respect to O plus VREL. From here, if I take this equation, I know that this is 0. So what is absolute velocity of P? This is omega of the disk, which is 0.4 K crossed with 0.45 I plus VREL is 1.2. Another thing we know from here is VREL. What is VREL? It is 1.2. And which is the axis it is pointing towards? It is parallel to Y. So it is 1.2 J. So this is something we know. Alright, so this is 1.2 J. So actual velocity of P is 0.4 plus 1.2. So this comes to 1.38. So therefore magnitude of absolute velocity of P is 1.38 meters per second. So we know this is 1.38 meters per second. Now the Coriolis component is asked. So we know that the Coriolis acceleration is nothing but 2 omega cross VREL. So what is omega here? 0.4 K cap. And we know VREL from here is 1.2 J. So what will this come out to be? This is 0.96. K cross J is minus I. So what does that tell us? Omega is a vector pointing like that. And then I have my angular velocity like that. So omega cross R will be minus J. Omega cross R if we take be minus J. So it is perpendicular to the slot here. At some other instant, its angular speed will be like that. So omega cross R will be like that. So it is invariably perpendicular to the slot. So A Coriolis is minus 0.6. The magnitude is asked. So magnitude of the Coriolis acceleration is 0.96 meters per second square. Now the magnitude of absolute acceleration of P is asked. So it is similar to the previous question with a small change. In the previous question we saw that this member is straight. So when we rotate with it, it has to have only one component of velocity and it can have only one component of acceleration. That is only J. When we are rotating with this, we will perceive only linear acceleration. Whereas here, if we see actually it is a circular slot. Although this is moving with a constant speed, which means its tangential acceleration is 0, nonetheless it has to go through this curved section, a circular curve, in which case there will be a tangent centripetal acceleration that will come into play here into ARL. So we will see that. So acceleration of point P or the ball P is acceleration of O plus omega cross R P with respect to O 2 omega cross VREL plus AREL. Now let us see the breakup as to what these quantities are. We know this is 0. Acceleration of p, this is what is our intention to find out. Yeah, so this is 0 and this is we want to find this out only. So do we know omega? We know omega. Rp with respect to O, we know. Alpha we have been given. In the question we have alpha as 0.1 in this direction. So alpha is also given. 2 omega cross VRL. We just calculated the Coriolis component. So that also we know. So the entire problem hinges on whether we know ARL correctly. So what is ARL? ARL is the relative velocity, relative acceleration observed by the observer rotating with this disk. ARL can have ARL tangential plus ARL normal or centripetal, let me say. Now, by virtue of VRL being constant, ARL tangential is 0. This is 0. This is because of the circular because the slot is curved, and since it is circled, it is easy for us. If it is not, otherwise we have to go for some intrinsic coordinate and do it. Anyway, so it will have some centripetal acceleration. So how do we calculate that centripetal acceleration? For a for an object which is moving along a circular path and has a velocity v, what is its centripetal acceleration? It is v squared by r. Or rather, if we want to see it like this, if there is an object and it is moving in a circular path, so centripetal acceleration will be omega cross r. Uh, Object, so this is omega cross object r. Now if this has v, velocity of o, velocity of o is omega r. So in such a case, to get omega squared r, v into v by r is omega. So omega squared is v squared by r squared. So omega squared r is v naught squared by r. So this is how we can gauge the centripetal acceleration. So do we know that v? This v is nothing but our VREL, because this object with relative to the disk, it is moving with this speed. So due to this speed, there will be a tangential acceleration acting. So this 1.2 squared by this r, radius of this curve, is what is that tangential centripetal acceleration. So it is 1.2 squared by 0.45. In such a case, ARL is 1.2 squared by, let me write it this way, VREL squared by r of slot, radius of slot, which is nothing but 1.2 squared by 0.45. So what is ARL? It is 3.2 meters per second square. Do we know the direction for this? It will be acting towards the center, which is minus I, minus x direction. So it is minus I. So the actual vector is this. So this is what ARL is. So the only difference between the previous question and this is that the slot is curved. By virtue of its curvature, there will be another component of acceleration acting, or at least being perceived by an observer rotating with it. So now it is just a matter of substitution. So let us quickly do that. So AP, I'll just take this. So this doesn't exist, so I'll remove this. Okay, so we know this is 0.4 K cross 0.45 I plus what was alpha in the question? It is 0.1 K cap cross 0.45 I. 2 omega cross VRL we have already calculated, I think. Yeah, here. We already have this, so we'll directly take that. So it is minus 0.96 I. And then ARL, we know it is minus 3.2 I. So what does AP come out to be? It will be minus 0.4 squared. So I've grouped all the I together, and then K cross I is J. So acceleration of P is minus 0.I plus 0.045 J. Again, calculations, I leave it for you to check some plus and minus here and there. But when I upload the sheet, I'll ensure that the calculations are correct. Since I'm solving it live, there is always a possibility of something. Anyway, so we have the acceleration of P coming out here. What is the magnitude? We can calculate of I squared. The magnitude comes out to be 4.23. So this is the magnitude. Yes, somebody had a question. Any questions? Yeah, yeah. Yes, yes, yes. No, no. See, angular velocity of this ball will be about what it is spinning about itself. If it is actually going along this slot with the rate of change of this line, with the rate of change of this vector, you can at best find out its linear velocity only. So I'll explain that a little bit. See, the question you're asking had a curve like that, a road like that, over which we have some axis, and then there is a car that is moving here. Let me draw the car also. So it is like that. Okay, so the position vector for the center of mass is like that. Now, if this is theta, theta dot is not the angular velocity of this car. Why? Because currently, in order for us to calculate the velocity of its center of mass, we are treating it as a particle at this instant. What does this tell us? Now, if this is r and we know theta dot, then we know this v, velocity of center of mass of the car. So r cross or theta dot cross r gives us v or center of mass of the car. Till this point, we are treating the car as a particle. Now, when we go into the analysis of how, when we consider 2 points in that very car and start analyzing its motion, that is when we will fix one point whose velocity is known, and then we will look at some other point. And in such a case, this car, it is like this, then at some other instant, it will be like that. Then some other instant it will be like that. So about its center of mass also it is having a rotation. So in order to capture this, it will be having some omega, right? That omega may be constant or not. So this omega is the angular velocity of this car. This theta dot is the time rate of change of this position vector. This position vector is the position vector of the center of mass of the car with respect to some datum. So it is not to be confused that theta dot and omega are two different things. Is it clear? Is it clear? Okay, yeah. See, ideally now, let us say now you might say that okay, the car is over here. Then at the next point, next minute, the car will be here. So it has actually rotated. It is undergoing general plane motion in the sense that from here it has gone here and then it has rotated like that. Right. So that would be the natural question that it is actually rotating while it is going. Are we considering that rotation into our analysis? The question. Even if we do consider, let us say, the car is actually undergoing general plane motion, fine. Now, in such a case, in order to analyze, would you say theta is the actual angular velocity of the car? Theta is only the position vector. It's the reference to the position vector from a datum. So the time rate of change of this only gives the time rate of change of this position vector. What is the time rate of change of a position vector? It is a velocity. So it only serves to give the velocity of one point. If we have to analyze the car as a rigid body now instead of a particle, we consider 2 points on the car. One, let us say the center of mass and some other point. Then there will be one position vector like that. The time rate of change of that position vector is its omega. If you remember the another question that you asked in the last session, let us say we have a rigid body and then we scribe a line. If I observe this line from a fixed reference, it will give me its omega. So this line, let us say I have got the velocity of the center of mass here. I've got the velocity of the center of mass here. Now I draw a line like that. How this line changes is what will give me its angular velocity. So let me call that line as the position vector itself with respect to some other point. The time rate of change of this position vector r vector dot is omega, which is omega of the car, which is not equal to theta dot. I hope now I have done some justice in explaining it. If it is still not clear, yeah, yes. If we want to find out the omega of the car, we need at least one velocity at one point. Then we need velocity as 2 points actually, or the position vector of 2 points. That is how we will be able to calculate it. For characterizing motion of a rigid body, you need velocity as at least 2 points, right? So with this, if we get to the center of mass's velocity, then we have to specify one more point whose some quantity, some kinematical quantity is known. And based on this relation, we can actually derive what omega of the car is. Yes. No, you see, if you tie a body to a rope and then swing it around, the body's angular velocity is not this. This is the position vector of that body. The time rate of change of this position vector only gives you the velocity of the body, linear velocity of the body. Now, in this same question, whether this ball is spinning about its axis or not is not a question that we are trying to address here. If it spins, if you see in the cosmic scale, if this is the sun, this is the earth. So when we actually calculate the velocity of the earth, we will be calculating its center of mass because distances are so large. We will treat that as a particle. Then when we confine our attention to this planet, then we will go about taking position vectors inside, scribing lines inside that rigid object. So it depends on what are you trying to analyze. Uh, is it clear? Okay. If it is not clear, you please feel free to raise your question, okay, at any time. Yeah. Okay then. So let us move on to the next question. So this is fine. And when I post this, I'll maybe write a brief about this and then post this PDF. All right. So let us look at this question. A rigid link QR. So we have QR as the rigid link, has angular motion as shown at the instant depicted. So this is having, so we see what we are doing is essentially we are solving similar problems with some key parameter changing. So initially we had a straight slot with only constant omega. Then we had a curved slot with constant omega with alpha and omega. Now we are having both and then we are having a straight slot. So all sorts of combinations once we do, we'll get the confidence to solve problems easily. So the link QR has angular motion as shown. So, okay, at the instant depicted with its peg P, peg Q connected to a slotted member. So this is a slotted member. Answer the following questions based on the data given with respect to the positive coordinate axis attached to the slotted member. So we have X here and Y. So we can see X cross Y, Z is pointing out of the plane of the paper. In such a case, this is also positive. So I will label omega RQ or QR as positive 1.75 k cap with respect to this reference frame. Similarly, alpha QR is in the opposite direction, so it is minus 0.4 k cap. So this much we know from the problem. All right. So this angle is given to be 30 degrees. So let us see what are the questions that are asked. If VQ is the absolute velocity of peg Q, then what are the component forms? So let us not do it by vector analogy. Let us do it quickly. So this will be, I know this will be my VQ, actual VQ. So I just need to resolve it into X and Y components. So this is X. So this component is X. Or why don't I take it here? If I take this here, this will become more clear. So this is X and I have this as Y. What is this angle? I know this is 35 degrees. So this will be 90 minus 35. So this is 55 degrees. So this is 55 degrees. So in which case, what is the X component? It is VQ cos 55 I, and this will be VQ sine 55J. So what is the magnitude of VQ? It is omega cross R. R is 0.95 into omega. So this is 1.6625. So magnitude of VQ is 1.6625 meters per second. In such a case, this will be 1.6625 cos 55. So I have this as 0.9395, and this is positive. So this will be plus. Whereas if I see this is opposite to this direction, so it is negative. So this is minus 1.36. All right. So now I know VQ vector is 0.95I minus 1.36J. If AQ is the absolute acceleration of the peg Q, then what are its X and Y components? So now if we were to analyze this, from the problem. Sorry, just a minute. So I will have one centripetal acceleration like that. And then I will have a tangential acceleration like that. Why that way? Because alpha is that way. So these are the two accelerations I have. So in such a case, can I resolve it quickly? So this is 35. If this is 35, this is 55. Or rather, an easier way to do this is, see, we have already, instead of doing this uh, resolution, what we can do instead is we can represent position vector of q with respect to r in the xy reference frame. If we do that, that is this position vector. If I express it in xy reference frame, then I don't have to do any resolution, vector resolution. So let us go about doing that. R of q with respect to r. What will this be? There will be a vector like that, and there will be a component like this. So if this is 35, this is also 35 degrees. So this will be 0.95 cos 35 minus I minus 0.95 sin 35 j. I don't know if it is clear. Let me try to explain it again. Right now we have only one way to find out acceleration of point q. Because we have been given alpha, we know acceleration, tangential acceleration will be like that. Because we know by virtue of omega, there will be a centripetal acceleration like that. Now to resolve all this into x and y component will be cumbersome because we have to calculate so many angles. Instead, what we do is, if we just express our actual position vector in the xy coordinate basis, then we simply have to take cross products. We don't have to worry about any vector resolution. So that is what I have done. So this is, if this is q and this is r, what I have done is I have taken it this way. So I have q here. So this is my negative x component and this is my negative y component. So that is what I have written. So this is r, q with respect to r is, what is this, minus 0.95 cos 35 minus 0.78 I minus 0.54 j. Once we represent this in this basis, then there is nothing, there is no vector resolution required. Now, if I were to go by relative motion analysis, what we have been doing previously without RFR, how does that come? Attaching a non-rotating translating axis at R. So here I attach a non-rotating translating axis with x and y like that. That x and y does not rotate. Now can I calculate AQ with respect to that? AQ I know is AR plus omega QR cross R, Q with respect to R plus alpha. Will there be any additional terms here? We have attached a non-rotating translating axis. It is not a rotating frame of reference. It is non-rotating. So there will be no Coriolis component, no VREL, no AREL. So we have only this to solve with the added convenience that AR is actually 0. In such a case, AQ will be, what is omega QR? It is 1.75 K crossed with this vector here, minus alpha is 0.4, minus 0.4 K crossed with again the same vector. So doing this is equivalent to actually resolving it using angles and finding out what the x and y components are. So let us do this. AQ is 1.75. So this will be 2.389 I. I hope the cross product thing is clear because it is explained in the lecture. So let me just quickly A cross, or why don't I do it with omega itself? Example for doing cross products quickly. So it is omega K cross R Rxi plus Ryj. If it is like this, what will this be? It will just be the product of these three terms with a negative sign. So it will be minus omega squared Rx, and then it will be minus omega squared Ry, and this will be preserved. I and j will be preserved. So this is a quicker way to do it. Professor has explained this in the lecture, so I hope you already know this. So that is how I am doing it. So AQ is nothing but I have put the minus up front. Now I just have to take 1.75 squared into what is that? Minus 0.78. These three terms I have taken. One minus is already there and this minus comes here. So that we can do quickly. So this will be my I. Then again I'll have 1.75 squared into minus 0.54 j. So we have taken care of this cross product completely. Now let us take care of this. When there is a single, not a double cross product, then we need to go for k cross j. The first and last will give you minus I, and this will give you positive j. So in such a case, it will be minus 0.4 into minus 0.54 I plus 78 j. So I suppose you already know this. If you solve a handful of problems, you will get the hang of it. AQ. So I can just add these up. So this is 2.29 I, and then plus 1.65 j, zero point 0.312 j. So I can add these up. So 2.29 minus 0.216. So 2.074 I, 1.65 plus 0.312 plus 1.965 j. So this is my actual acceleration of q, which I would have done it by having resolved it into vectors, but this is one way to do it. So this is 2.074 and this is 1.965. So now the magnitude of velocity of peg Q as observed by observer rotating with the slot is asked, and then magnitude of angular velocity of the slotted member is asked, Coriolis component is asked, and magnitude of the angular acceleration is asked. So as in essence everything is asked. All kinematical quantities of all the components are asked. So I won't solve it threadbare. When I upload this, I will solve it because otherwise I'll just be doing this throughout the session. So we'll take some other questions also, but I'll just briefly write down how to do it. So velocity of Q as measured along the slot. What does this mean? So this is implying what is VREL is what is asked. Magnitude of PQ as measured along the slot. So we know actual velocity of Q. So this is a known quantity. And then what is the position vector? Position vector of Q, RQ with respect to, let me call this point O. RQ with respect to O is nothing but 0.75 I. So attaching the rotating frame of reference with its axis parallel to the slot for straight slotted members makes it easier because there will be only one component in the position vectors. So it is easier to take cross products. So R of Q with respect to O. So we know R of Q with respect to O is nothing but 0.75 I. Now I know velocity of Q, the same drill, velocity of O plus omega of the slotted member. Okay, omega of the slotted member cross R Q with respect to O plus VREL. And what do we know about VREL? VREL will be along I because that is parallel to the slot. So this will be along the slot. Therefore, VREL is VREL I. Then we just need this is 0. It is just a matter of substituting. One unknown is this, another unknown is the magnitude. So with these two you will be able to find. Similarly, acceleration of Q now will be acceleration of O plus omega plus alpha, which is unknown at this juncture, plus 2 cross this VREL, which we found out earlier, and then AREL. And what do we know about AREL here? It is a straight slot, so AREL also has to be tangential to that slot, which means AREL will also have only I component along the slot. So AREL has only I component. I needn't write that. And then again grouping I and J terms, you can solve for the unknowns. So are there any questions at this instant? Because I figure we have been doing similar problems time and again. It gets a little dry. So if there are any questions, you please feel free to ask. In the meantime, we'll look at the next question. And when I upload the sheet, I'll solve this completely and I'll upload. So these things, it can be calculated. So let us see this problem. So this is similar to the problem that we did initially, except the disk was horizontal. Here it is vertical. Another difference is that that disk was spinning about its center, whereas this disk is rolling on the floor without slipping. So a circular slotted disk, this is the circular slot. So this is a circular slotted disk, rolls without slipping on the ground with an angular velocity and angular acceleration of omega equal to 5 and alpha equal to 2.5 in the direction shown. So both are shown this way. So essentially, if my x and y is like that, omega and alpha both are negative here. It is known that the pin is moving from A to B with a constant speed of 1.5 measured relative to the slot. So this pin, the red pin is moving like that, and its speed is 1.5 meters, which is constant. So VREL is constant, and it is moving along the slot. And this slot center is also O. So ignoring the gravitational effects, answer the following question. So what is asked? Magnitude of the absolute velocity of P, Coriolis component, and acceleration is asked. So let us see how to go about doing this. Now we know here that omega of the disk is minus 5 k cap. Alpha of the disk is minus 2.5 k. Both are clockwise, so it is pointing into the plane, and since x cross y is positive out of the plane here, that is why these two are negative. Okay, now we need to find out the absolute velocity of point P, or the ball or object, whatever that is. So if we go about doing this in two ways, let us say that we attach the rotating frame of reference at disk's center. As given in the question, we have attached an xy axis to the center of the disk, and that axis is rotating with the disk. In such a case, how will we go about analyzing Vp? Vp will be Vo, velocity of O, plus omega of the disk cross VREL, cross R of P with respect to O plus VREL. So what is now comes the interesting part. Till now, what we have seen is when we do this, V naught is actually 0, because it is either hinged or fixed somewhere, so it will have no velocity. Whereas in this case, it will be having a velocity, which we have to find out using our kinematical relations of circular motion. So what is the velocity of this point? If omega is given, this is r. If we know omega, so omega r is the velocity there, right? So what will that be? It will be, so this part will be minus omega of the disk. What is it? 5. Minus 5k cross, what is this? This is 1.5 I, because this is the instantaneous center of rotation. So to calculate the velocity of any point on this disk relative to this point, we need to find its position vector and take the cross product with omega. So this is 1.5 I, so this will be 1.5 I. I could have simply done this. I can see that it is rotating like this, so it will be omega r. But I'm just doing it by vector analysis to show you something. So this is minus 5 k cap cross 1.5 I plus, now omega of the disk is minus 5 k cross r of p with respect to O. At this instant, this point is over here. So what is this vector? It is 1.1 I, 1.1 j. I'm sorry, this is also j. This is not I, this is j. Sorry about that. And this is 1.1 j. So this is 1.1 j cap. Plus, what is VREL? It is given that its speed at this is constant, which is 1.5. So it is 1.5 I cap. So VREL is 1.5 I. So this is my VREL. Okay. So what will this come out to be? It will be k cross I is j Let be J. I'm sorry about that. So this is 5 into 1.5 plus 5 into 1.1. So this is 13 I plus 1.5 I, which is 14.5 I, absolute velocity of P. Now here we attach the rotating frame of reference to the disk center to this point. Instead, if we were to attach it here, the answer should come out to be the same. If we attach it here, what will our equations be? It will be velocity of this point plus omega cross r plus vrel. This omega cross r, this r is actually having two components. One is like this, one is like this. Both added up together. So if we see, these two will get added up into one vector when we attach it. So it will come out to be the same. I hope this is clear. If it is not clear, please do ask. Let us say that let me write that instead. Instead, I attach the RFR to the instantaneous center of rotation. Let me call this O prime, or let me call this something else. Okay, O prime. In such a case, velocity of P I know is velocity of O prime plus omega of the disk crossed R of P with respect to O prime plus vrel. What has changed? Now these two quantities get contained within R naught, and this goes to 0 because this is the ICR. So essentially it is the same thing, just that this was split into two components. So velocity will come out to be the same. It is clear that velocity will come out to be the same. So the magnitude of velocity is 14.5 I, or meters per second, in the right direction. Magnitude of the Coriolis acceleration of P is, we have done this umpteen number of times. So what is this? It will be 2 omega cross vrel. So it is 2 into, what is, it is minus 5k cross, I think it is 1.5 I. So it is 10, it is just 15. K cross I is j, so it is minus 15j. Why? Because my vrel is like that, omega is like this. So omega cross vrel. Okay, it has to point positive, it won't be minus. Why it is coming? K cross I is omega. Yeah, sorry, omega is pointing into the plane of the paper. So it will be positive, it will be negative j only. It will be like that. Yeah, okay. And then what else is asked? The absolute acceleration of point P is asked. This also, similar to our velocity, we can do it in two ways. If we attach, let me write it here. If we attach the RFR to disk center, so acceleration of P will be acceleration of O, which is the center of the disk, plus omega alpha cross RP with respect to O is 2 omega cross vrel plus ARL. Now what is different here? ARL we know how to calculate. We have the recipe because it is a circular slot, but it is moving with a constant speed. So it will have no tangential acceleration, but it will nonetheless have centripetal acceleration. What will that centripetal acceleration be? It will be VRL squared by R of the slot, radius of the slot, which happens to be the radius, which is not the radius of the disk, which is 1.1, because this is also having center at O. So far, so good. Now, this we can calculate. This we have just calculated. Alpha and omega, it is just a matter of substitution. Now, acceleration of O. If we take acceleration of O in this problem, since non-zero alpha is there, this will be alpha cross R. This will be this alpha cross this R. So this point is having an acceleration like that. Whereas if we were to do the same thing by attaching the rotating frame of reference to the ICR, in our previous analysis, this quantity was 0 because it is the ICR. If we write the same for acceleration, this will not be 0. As we saw in the previous session, it will have a centripetal acceleration which will be pointing towards the center of this curve. So it is just a matter of substituting that and we'll get the value. So I don't want to go on doing cross products now. I suppose this is getting a little boring. So if there are any questions in what we discussed, I'm happy to take them now. Any questions about what we discussed in here, or any questions about the previous sessions, or anything about the subject matter in general? Something that is not clear? Okay. Well, in that case, this is the only question I have, so I may well go ahead with while solving it then. So we have calculated these two. We have to calculate absolute acceleration of point P. So what will this come out to be? Acceleration of P is alpha, which is what here in this problem? It is minus 2.5 k. So it is minus 2.5 k cross 1.5 j. This is just this part, the acceleration of the center of the disk. And then we have this k, right? Yeah. Cross 1.1 j and then minus 2.5 k cross 1.1 j minus 15. We already got this as minus 15j. So this will be minus 15j and this will be minus 1.5 squared by 1.1 is my radius and this will be along j. So it is just a matter of solving it. So I'll upload this after solving this. Other than that, if there are any questions, I'm happy to take them. Is it clear what we discussed? Are there whatever questions we saw? I suppose with this background, you'll be able to attempt the assignment questions because those are also similar in nature. So initially what we do is we take, first of all, we gauge with velocity and acceleration of which point we know absolute velocity depending on its connections. From there, we see the same point from a rotating frame of reference in order to obtain kinematical quantities for the rotating member, the slotted member. So that is the essence of doing this. Anyway, I have run out of questions now, so I don't want to solve this right now. I'll rather upload it. When I do upload it, I'll solve this and upload. So if there are any other questions, I'm happy to take them. Okay, well, if there are no questions, then I'll anyway upload this sheet with its calculation. So if there are no further questions, I'd like to call it a day, if that's fine. When will you upload this? I'll upload this by tonight. As I have been doing for the other sessions also. I'll upload this sheet. I will upload in a matter of an hour or so. And the video which I'm recording right now, that I'll upload by tonight in Swayam app. Yes. In Swayam app, on the left side, you can actually see that live session folder is there. It's a common folder which has the links to all the previous videos also, including this one, which I'll upload now. And it also has a folder link where these PDFs are available wherever I have solved them. So those are also available. I suppose you have access to that. So anything else other than that? Is it clear? Okay, thank you. If there are no further questions, then I'd like to call it a day. So I'll see you in the next session. So next session will be on planar kinetics. So till now we have been seeing how to evaluate kinematical quantities, namely angular velocity, angular acceleration, linear acceleration, velocity, and so on. So the purpose of doing this analysis is to be able to design mechanisms, etc., where we need to find out what will be the input and output. So once we give one force, what will be the acceleration developed, or the other way around. So we need to learn how to tie these kinematical quantities up with kinetic quantities. It's a weekly class. Yes, it's a weekly class that is conducted every Friday, 6 to 8, since the course has started. So we are on the 10th week right now. So there are 2 more weeks to go. So in the next week, we'll be looking at 2D kinetics, where we will tie these quantities, whatever we have calculated till now, to kinetic quantities to kinematical quantities, namely angular momentum and linear momentum, force, and torques. So after that, the week after next, we will be looking at the last topic on 3D kinematics. Right now, we have confined our attention to 2D space with the assumption that, not the assumption, for problems where the axis of alpha and axis of omega are common. If you see in all the problems that we solved till now, wherever we have considered alpha and omega, it is always k cap, either plus or minus. We will relax this constraint now when we go to 3D objects, so it can have a magnitudinal change as well as a directional change of omega. So what implications that has on the 3D kinematics of objects, that we will explore in the session that comes week after next. That will be the last session for this course. And then depending on the need, we will maybe arrange for one just a common doubt session for addressing all the queries that have come throughout the duration of the course, not specific to any specific week, but to the course as a whole. But that will depend on the need. So other than that, I have nothing more to say. So if there are no further questions, so I call it a day. So I thank you for attending. Anything else? Thank you. Thank you.